convex hull is a truly classical multidisciplinary concept. One definition of the convex hull of a planar point set S is that it is the complement of the union of all half-planes that contain no points of S. In a view suggested by Fisher inspired by Adelsbrunner and Mücke, the whole space is an infinite piece of ice cream, and the points in S are chocolate chips in it. Now imagine that every line in the plane is an infinite length knife. Using the knife, you can cut out and eat a whole half plane of ice cream. Suppose though that you are allergic to chocolate and can only eat half planes that contain no chips. Then the convex hull is the part of the ice cream that is left after you have eaten with the knife as much ice cream as possible while never eating out any chips. Convex hull is the first step towards determining the shape of the point set.
However, the shape approximation provided by the convex hull may be poor. This is because the knife is quite a crude tool, not given the ability to carve out pockets into the shape. A finer ice cream eating utensil is a scoop, which is a ball of some radius alpha. Adelsbrunner, Kirkpatrick and Seidel introduced the notion of the alpha hull of S, the part of the ice cream that remains after you have eaten out all radius alpha circular scoops of ice cream that contain no chips. The boundary of the alpha hull consists of circular arcs of radius alpha. The alpha shape is a straight line version of the alpha hull, with the arcs replaced by straight line segments.
Let us use this Java applet to see how the alpha shape depends on alpha. The value of alpha controls the level of detail with which the shape is reconstructed from the point set. For larger alpha, fewer pockets are carved out. In the limit, as alpha tends to infinity, both alpha shape and alpha hull become the convex hull of the set. This means, of course, that alpha hull is a generalization of a convex hull. Another generalization of convex hull, introduced by Cole, Sharir and Yap, is the K-hull. For a given integer k, the K-hull can be obtained by a cheese knife with K holes in the blade. Imagine that equipped with the cheese knife, you can eat any ice cream half plane as long as it contains at most K chips. The chips themselves are not eaten. They stay in place as the ice cream half plane is removed. The K-hull is then the part of the ice cream that remains after you have eaten out all K full half planes with the cheese knife. Let's see how the K-hull depends on K. For K equals 0, the K-hull is just the convex hull. As K grows, the K-hull gets deeper and deeper into the points. For this behavior, K-hull is known in statistics under the name K-depth contour. The K-hull is actually the level set of half-plane depth function. The half-plane depth, as well as many other notions of depth developed in the field of statistical data depth, captures the notion of interiorness of a point with respect to S. Or, in other words, assuming that the points in S are samples from a distribution, how deep the point is inside S or how close it is to the distribution's maximum. For instance, the points over here belonging to K-hull for higher K are deep. These points are not. So let's now do inventory in our kitchen. The knife is used to obtain the convex hull, the complement of the union of empty half-planes. The scoop of radius alpha is used to obtain the alpha hull, the complement of the union of empty alpha balls. The cheese knife with K holes is used to obtain the K-hull, the complement of the union of K full half-planes. It is natural to define a generalization of both the alpha hull and the convex hull. Call this generalization the K-order alpha hull, as the complement of the union of all radius alpha disks that contain at most K points from S. In ice cream and chips terms, the K-order alpha hull can be obtained by scooping out ice cream with a colander having K holes. The K-order alpha shape is a straight line version of the K-order alpha hull. Let us see how K-order alpha shape depends on K. For K equals 0, the K-order alpha shape is just the alpha shape. With larger K, the K-order alpha shape digs deeper into the point set, with the amount of digging controlled by K. In a sense, K-order alpha shape shaves off locally about k points from the boundary of S. If the shaped points are outliers, this may be a good thing. Indeed, here is an example we concocted to demonstrate a reasonably good job that the higher order alpha shapes may do. This is S, and this is the alpha shape of S. Suppose the two outliers were added to S. Because of the outliers, the alpha shape is missing the hole, an important feature of the shape of S. Now, using k-order alpha shape with k equals 1 or 2 brings the hole back. Our next example justifies the potential usefulness of k-order alpha shapes in statistical data depth analysis. Suppose that this set S represents samples from some distribution. Here are the k-hulls of S for different values of k. Observe that these points are classified by the k-hulls as being deep inside S. This does not look as a correct classification because these points are unlikely to be samples from the same distribution as S. At the same time, using k-order alpha shape with alpha less than infinity allows one to identify the depth contours separately inside each cluster of points. Now these points have small depth, while these have higher depth. To summarize, k-order alpha hull is a generalization of two generalizations of convex hull, alpha hull and k-hull. As a generalization of alpha hull, it may be useful as a shape reconstruction tool robust to outliers. As a generalization of k-hull, k-order alpha hull may help to identify regions deep inside a multimodal distribution. Similar generalizations are possible for other graph structures and point sets. One may define, for instance, k-order alpha and beta skeletons and beta shapes. To feel what they are, we invite the viewers to play with our applet at the address shown at the bottom.